presentations.
Yes. And I just want to remind you, Matt did a fantastic job last time. So,
I know, I'm nervous. I'm
yeah,
nervous.
I mean, we missed the famous words from Toby. We were blessed. We even learned some Chinese on that. We got lots of good comments on YouTube too. So
Nice.
no pressure.
Yeah, it's going to be a tough act to follow. But today I'm going to be talking about chapter 13, loading and pre-processing data with TensorFlow. So before diving into that, I wanted to talk a little bit about why this is important and why there's a chapter on this, because I don't know, you can initially think you can just load all your data into RAM and not have to load it in special ways. So let's say that you have a warehouse full of packages and you only have one truck to transport all of the packages to the office building. So the only way for you to successfully do that is if you load the truck multiple times and go back and forth, transporting one batch of boxes to the office building, going back, getting another set of boxes and bringing it to the office building, because you can't fit all of the boxes into the truck at one time. So that's the kind of the whole idea behind this chapter, and the whole idea behind loading and pre-processing, that if you imagine that your warehouse is similar to your storage or your data stores of images or text or your data source, and the office building is like your RAM and your computer, you can't take everything at once and store it in RAM. You have to strategically load data and process data. So that was just an intro, but today I'm going to be talking a little bit about the contents of this chapter, which was the TensorFlow data API. So different transformations, shuffling, data serialization, prefetching, and protocol buffers. And then I'm also going to be talking about different pre-processing that TensorFlow and Keras support, like one-hot encoding, word embeddings, and pre-processing layers. And then finally, I'm going to be talking about TensorFlow, the TensorFlow dataset project, which is TensorFlow's very nice way of packaging really commonly used datasets like MNIST or CFAR or any of the datasets like that. I also want to show a little bit, if we have time, a little bit of our own code for image pre-processing, because I mean, that's what I have the most experience with. And a lot of this is focused more on your normal machine learning features rather than imaging or NLP. So the first thing I want to talk about is what actually is a data set. And TensorFlow defines a data set as a sequence of items. So if you look at these code snippets below, you can create a data set, a very basic data set, in two ways. The first way is assigning a TF variable. So assigning X to be TF.range10, and that means that you'll just assign 0 through 9 tensors in that variable. And then to make the actual data set, you just call the data set from TensorSlices function on your variable, and you get this output below. So you'll have each item in the data set to be its own tensor with the values that you inputted in the variable. On the right-hand side, you can create kind of the same thing, except you just call range on the data set function directly. So these amount to the same thing. This is just less code, but the output is the same either way. Another thing you can do with data sets that TensorFlow lets you do quite nicely is you can do various transformations, and then you can also chain these transformations. So in this code snippet, we're assigning data set to the dataset dot repeat 3 dot batch 7. So I'll go into this part by part, but I want to mention that before going into this, that whenever you call a chaining function, what it's doing is it's not modifying an existing data set, it's returning a new data set. So it's important to make sure you're setting, you have this equality in your code where you're assigning the return values of these functions to a variable instead of just calling it on the dataset object itself. So the first thing, the first function is the repeat function, and this is kind of, you can kind of infer what it does. It just repeats the values in the data set. So let's say, so if we go with a data set from before, which was just the tensors 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, this would just kind of multiply that by 3, but not actually. What's cool about this function is it doesn't actually take up more space. It just adds a repeat clause to the data structure that says that it should be repeated 3 times when being used in a machine learning model. And then batching is another function that will batch the values. So if we look at the previous slide, we see that they're all individual tensors. But if you call a batch function on the data set, it will batch the function into the number of data points from the parameters. So, and here we have the batch size of 7, so it's batching 7 values together. And right now you can see it's sequential because we didn't call any type of randomness on it. So it's just dividing it into 7 even parts. And then if you have a remainder, it'll make the last tensor in the data set that remainder values. So we have 7, 7, 7, 7, and then 2, because that's the remainder. All right. This is just another visualization of kind of what's going on under the hood in this chaining function. So we have the first thing from tensor slices, where we built that initial data set in 2 slides previous, then called the repeat on the data structure, and then we batched it. And then finally, we have our data set. And again, this doesn't necessarily modify the storage. So the tensor slice, the data from tensor slices going from 0 through 9 has the same memory, or about the same memory footprint with all of these training operations, which is just another way that TensorFlow optimizes your storage. Because imagine if you had a really large data set that you wanted to repeat multiple times, it would take up a lot more storage than just replicating 10 numbers 3 times. Another thing you can do is various mapping operations. So you can use lambda functions, which are described as kind of ghost functions, and they apply their function to each value in a data set. So if you call the map function and call this, which will just multiply everything lambda x, so you're saying for every x multiply x by 2. So it's just multiplying every value in the data set by 2. So if we had the data set before that was dot repeat 3 dot batch 7 and multiplied every value by 2, we get 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and then it repeats again. You can also use lambda functions to filter data sets. So if you have a huge data set and you only want values less than 10, you can do that with a lambda function. If you only want values in between a certain range, you can do that with a lambda function, which is pretty useful. It's a lot like filtering in pandas, but using a different API. The next thing you can do is also unbatch. So if you want, it's an experimental function still. I think they just released it in the newer version of TensorFlow as a non-experimental function, but if you have a data set that is batched, you can call unbatch and it will unbatch the data set. So make each data point its own individual tensor. Then also in this snippet below, you can also take the take function, which is if it just lets you take certain values off the top of the data set if you don't want to load the whole thing into memory. Another really, really important thing with TensorFlow datasets is shuffling. And this is important because if you remember, I think it was chapter 4, we talked about stochastic gradient descent algorithm. And we noted that the algorithm only performs optimally when the data is completely randomized. So it's really important. So we saw in the examples before that the data wasn't shuffled or randomized, and it's really important to randomize that data set. And shuffle works in a pretty cool way. So what it does is you have these parameters. So the buffer size, which I'll talk about in a second, and the seed. So the seed just makes your experiments reproducible. So if you set the same random seed in different experiments, you'll be able to achieve the same results in the same data distributions. So what buffer does is it queries the first So let's call this parameter n. So if in this case it's 3, so it'll query the first 3 items, and then it'll randomly take from the 3 items here and put them into the shuffle data set. So it creates a buffer in memory. So it's not doing it all at once, which is more memory efficient than the alternative of just loading everything and randomizing. It also, you don't have to call repeat again because the data set is already there. So this kind of data set equals TF, this function, if you could change the shuffle, you could change the shuffle operation to the end of this, and it would achieve the same result, which is a really nice functionality of this API. Another thing that's important to mention is parallel processing. So if we talked about, remember in the first analogy, we talked about how there was one truck transporting the packages from the warehouse to the office building. But if we looked at it from a parallel processing perspective, you could use multiple trucks to take the packages from the warehouse to the office building. And that would just make sense that would improve the speed of the unloading process of the packages. So if you can imagine, if you think of these roads as threads in a computer or resources or CPUs, the more you have, the faster it will go. So when we also have this idea of prefetching. So this allows data to be prepared before used in a model. So without prefetching, this is kind of the sequence, assuming you have CPU and GPU resources available. So normally you train the machine learning model with a GPU if it's available, and you do any pre-processing with regular CPUs. So in a normal sequence that we were talking about before, you would prepare the data, do any pre-processing or data transformation in this step, and then you would transmit that to the GPU for training. Then you'd prepare a second data set or a second batch, use it in training, and then it would go forward like that. With prefetching, you would do these steps in parallel. So instead of sequentially preparing and using the data sets, you would prepare the first data set, then you would use it while you're preparing the second data set, then you would use it while you're preparing the third data set, and so on. So it closes this time gap, and it really lets you optimize your compute resources and not waste anything by closing these gaps. Again, and then also if you have multiple CPU threads, you can close the gaps even more and just use more computing power to load and process your data. And this is supported inherently in the TensorFlow API. So you don't have to do any fancy multi-process coding to get this to work. If you have the resources available, it should work as expected. And here are just some other important functions that weren't dove into that deeply, but just wanted to mention the cache function, which will save a data set into memory. This is not necessarily useful because if you cache a really large data set, you're gonna use up all your memory. You can concatenate data sets together. So if you have 2 data sets and you want to join them, you can zip data sets, which it's not like zipping or compressing. It's like you can change their types. Window, which is taking a small portion of the data set, reducing, you can hard, flat map, and all of these other functions are easily implementable. And if you have any questions about them, feel free to ask me. These 2 at the bottom, I thought were 2 of the most important. So there are other constructs in Keras and TensorFlow called like a data generator, or again, we talk about a tensor. So if we have a group of tensors or we have a data generator, we could create a Keras data set, data structure from a data generator or from a group of tensors. So the next thing I want to talk about is data serialization. And data serialization is kind of a hard topic to explain. So I kind of try to imagine it. If you've ever seen, has anyone ever seen Star Trek? maybe. So basically in Star Trek, they have this teleporter machine that will, the way they describe it in the show is they convert you to like energy. So they convert your body to energy and then transmit the energy to a different pad. So the whole process is you're on like this surface, you're transported to energy, some kind of compressed energy form, and then you're de-energized and you're now on this pad. So that's kind of what's going on in this serialization process when you serialize and deserialize data. So the real definition of data serialization is when you convert the state of an object in your code to a byte stream. And that means you're just essentially compressed. So you're compressing it into a smaller use case or a smaller file. So you don't have to use any memory overhead to keep recreating the same object. And this is really useful when you're using an object multiple times. So if you have a class with the same parameters that you're just going to use over and over again, it might make sense to serialize it and deserialize it instead of recreating it every time you need to use it. So the main point of that is that this process just saves space and time. So that goes into the TF record format, which is the TensorFlow API's preferred format of storing these data sets. And each TensorFlow record contains the length of the record, a checksum for the length, the actual data, and a checksum for the data. And a checksum is just kind of a verification method. So to check for data corruption, but it doesn't check for data authenticity. So let's say like the data was downloaded wrong or something like that, then the checksum wouldn't align with the length. And it would throw an error that the data was corrupted. So that's what the checksums are for. And these are what each TF record contains. And the TF records are pretty easy to use if you're familiar with just using Python, just writing text files or using files in Python. So you have a class called a TF record writer, and you just call it very similarly to how you would call a normal text file or any other file you're writing. The biggest thing here is this B, and it took me a little bit of research to figure out what it was, but it's telling the computer to write this in binary and not as text. So byte stream is just a binary stream. So when you serialize, so this is serializing this data essentially. So you're just writing this to the TF record, and then after you exit this block, the record would close. And then to read, to convert a TF record to a data set is very simple. You just have the path or paths to your TF record, and you can call this function, the TF record data set, on the file paths, and it will turn your sequence, your individual or sequence of TF records into a data set. So they're very easy to save and load for use in your machine learning models. Another thing you can do is compress them. So you can add this TF record option to your writer or reader. So if you write it and let's say you store it as a gzip compression, you have to make sure to also read it as a gzip compression, or else it would throw an error that it was an unrecognized format. So compression is useful for a variety of reasons, but would essentially also just save space.
Can you do this to like data sets?
Yeah.
That looks really cool.
Yeah. I think it would be interesting to try this. I'm not so. The big thing that I was coming to soon is that I haven't really found anything about how to do this with images, like store an image as a TF. I think you can do it, but I'm not sure how. I haven't really found anything on that yet. So that's what I wanted to explore next. But moving forward, so you can store any type of binary data in the TF record format. So that's why when we're writing, we have this B, because that stores it in binary. But a protocol buffer is the most popular use, and protocol buffers are actually really popular right now. They're a construct built by Google, and they essentially just define their serialized binary format. So I can go through. So this code is just saying that we have a person. And so syntax equals proto3. So that's just saying that you're using the third version of the protocol buffer encoding. This is just creating a new protocol buffer called person, which will save in a .prot or .proto file. And these values are just declaring the fields and assigning a key to the field. So you're having a name with key 1, ID with key 2, and a string email with key 3. And here you're just defining the type. So string, int32, and repeated string. And that's just a not bounded string. It's important also to, I'm just going over this briefly, but you have to install a couple of extra packages, including the protobuf compiler, to be able to use this accurately. So for example, when using protobufs for features, that before was a person protobuf, but TensorFlow contains useful protobuffers for machine learning models. And the way to do this is first, you want to create a protocol buffer for an example protocol buffer, which contains additional protocol buffers. So protocol buffers can be nested, and each example is one instance in a data set. So your whole data set, if you're encoding your TF records and with protobufs, would just be a sequence of examples. And in those examples, you'd have a sequence of features. So that's what you're just defining down here is the protocol buffer. And then you can write the protocol buffers as really serialize them really easily and write them to TF records. So these can also be loaded as CSVs or Excel sheets or any other TSVs or any other file formats you want.
It seems like with the protocol buffer and the TF record, you're just saving it differently rather than actually, yeah, I see. Yeah, that's actually good.
Yeah, I think the idea, the reason why they like or stress protocol buffers is because it's like a standard, so that it would be easier to reuse and reproduce and not have to deal with the because the other ways to serialize could be unique to an institution or a company or a person, and they're probably, if you use protocol buffers, you don't really have to worry about figuring out how to serialize and deserialize the code. So here, when you're loading the here is just you're describing your features. So you can have a fixed length feature, a variable length feature, your data types, and then you just parse the example into the protobuf. So this is a way so that you don't have to do this manually. So if you see here, right here, we're actually manually assigning the values Alice, value, their feature 1, 2, 3, and their emails. However, here you can write a script that, let's say you have a CSV file, you can write a script that defines these fields and then read the CSV file and assign it directly into the TF record and serialize it on the fly, which is really useful when dealing with big data sets that you want to convert into TF records. Now we're going to go on to the pre-processing part of the talk, and this is the second part of 3. So we've learned a lot about pre-processing in the beginning when we were doing the basic machine learning models. In I think chapter 2 and 3, we were talking about the scikit-learn standard scalar class. And then we talked about batch normalization, which you can put inside your deep learning model. But what if we want to pre-process the features on the fly? So with standard scalar, if you remember, that was part of the pre-processing pipeline. And batch normalization could be used as a pre-processing layer, but isn't always the best choice. But what's nice is that Keras and TensorFlow allows you to define your own layers. So this is a Lambda layer. So just like we talked about Lambda functions, this just adds this layer that will do your Lambda function on your input features. So this is normalizing. This is doing the normalization for the input features in the Lambda layer. But TensorFlow has, so I want to go back and reference Matt's talk for a little bit, how he greatly explained the inheritance of the class structure. So you don't have to define your Lambda layer, because Keras, you can create a layer class that inherits from the parent keras.layers.layer class. So these layers only have to call two functions, adapt and call. And you have to make sure to call the adapt function before the call, because what adapt does is it learns, your mean and standard deviation from one data sample. And then when you call the function is automatically called in the model. So now when you look, so this layer is standardizing the input features of your model. Another thing that we can look at is one-hot vectors, and this differs from one-hot encoding. So if we remember, one-hot encoding is when we take a sequence of categorical variables. So let's say we had these five geographic features. In one column, we would separate them into 5 columns with only ones and zeros value if they corresponded with the variable in that column. But with the new TF dataset form and TF record format, this might not always be the most efficient, because the whole impetus behind TF datasets and records is saving space. So you could have so let's say you have a dataset with 10 vocabulary words, or in this case, we have 5 vocabulary words. It's very possible that your first data sample will have these 5, but an additional number of data samples will have like 7 or 8 data samples, which doesn't really, which starts this problem where you might not have labels for all of your data. So that brings in this concept of out of vocabulary buckets, or OOV buckets. And they're kind of like, they're buckets that act like these categorical variables, but they can store any number of values. So if you have, let's say you have these 5 types in one data sample, and then your next data sample has 6 data types. So these 5 plus one additional one, it will assign the additional one to the OOV bucket that you created. So it's just a way to catch. So let's say you're expecting 10 input features. It's just a way to catch them without having to load them all in memory. And this saves space a lot, because if we just use a CSV, like a normal CSV file, the null values and the NA values in the table are actually just storing extra space. So when you have a really large data set that's very sparse, you're really just wasting memory. So then you can vectorize them as well. So you can look up, your tables very easily. And when you print the tensor, it looks very similar to a one-hot encoded tensor. So the next thing I want to talk about is word embeddings. And word embeddings are a trainable vector that represents a category. So I had a very hard time understanding, to be honest, word embeddings when I first went over them. So I watched a crash course from Google, which really helped. So word embeddings are just a dense layer that you put in your model with trainable weights. And it's a hidden layer most commonly used in NLP. So to explain what word embeddings are, let's say we have this data set of movies, and you're trying to arrange them, and you're trying to figure out, you're trying to separate them into categories. And the way these are separated right now seems to me to be cartoon movies to maybe more adult movies. But you could also rearrange them as action movies and family movies, or you can arrange them as sci-fi and fantasy to, I mean, they're all sci-fi, I guess, and fantasy, but you can rearrange them in multiple different ways. And it doesn't really give you this one-dimensional embedding, doesn't really give you a great picture on the different categories of the data. But let's say you had a 2D embedding where you increase the dimensionality of the vector. And now you have much more categories and much more ways to define the different movies. And this way, you can separate into children, blockbuster, art house, and adult films. So this 2D embedding is more accurately describing the sequence of movies, just because we added another dimension and added another layer of understanding to the model. So what embeddings really are is not just two, but you can have n-dimensional n-dimensional embeddings where the categories are trained while you train the model. So that's the idea behind embeddings. And these are used a lot in NLP when you have like a corpus and a lot of different words and categories. Another thing that Keras can do, which is really nice, is just like in scikit-learn, where we have pre-processing pipelines, we also have a Keras pre-processing pipeline. So let's say we have two layers that we define, the normalization layer and the discretization layer. We can pipeline them together in the pre-processing stage and normalize them on the fly. And then you just call, the pipeline is just a layer, so you have to call the adapt function on a data sample to begin as well. So now I want to talk about other pre-processing tools and more ways to save space, and talk a little bit about model deployment and real world applications of a model. So these tools, Apache Spark, Apache Beam, the TensorFlow Extended, are all really scalable distributed analytics platforms. Spark is like, lets you load databases, is like pandas, so it's really just a really fast version of pandas. Beam acts similarly, and TensorFlow Extended has some of the same functionality as Spark and Beam, but in the TensorFlow API. So one reason you might want to use Apache Spark to pre-process your data, or any of these tools to pre-process your data before deploying your model, is that when you have these layers, let's say you have a data set, and since these are model layers, your data is being pre-processed during model training. So let's say you have a huge data set, you're essentially just pre-processing different batches in the same data in every epoch multiple times, if you don't do it beforehand. But if you use Spark or any other of these tools to pre-process your data before training, you only have to do it once, which saves space and time and saves your memory. Another thing, you can also do kind of a combination of these tools. So let's say you have a model that you want to deploy in production, and you have a lot of data to train it on initially, but you want it to continuously learn from user input or clinical input or whatever input. So you pre-process your initial data using Apache Spark, let's say, and then once you deploy the model, you can add the pre-processing layers so that it learns with new input data. So that way it's not totally saving memory, but it's saving some memory, because the limitation of these tools is that you have to manually do it. You have to run the code to pre-process it once. But with the layers in between the model, you don't have to worry about that anymore. The last thing I want to talk about is TensorFlow datasets. And TensorFlow datasets are an easy, commonly curated dataset. So like MNIST. So for the MNIST, you can just load the dataset. So there's there's a whole package and a whole list of documentation of different data sets. You can really easily just split it into training and testing just by calling the train and test keys. You can load. So here they're loading the model as supervised equals true, makes it not just load the images, but also load the labels, calling prefetching. So it's using that parallel processing tool to load the data before, and then you can feed it directly into a model. So however you define your model in these dots, compile it and run just like we would in any other model. So that's all I have in the PowerPoint, but now I wanted to show a little bit about how I pre-processed my code. So this is a model for detecting race in mammograms. So here are all my, you guys can see my screen, right?
Yes. Yes.
So
this is a very spicy topic right now.
Yeah, yeah, it is. So here's all my dependencies. Here's where I'm filtering the data. So we had different data frames from different cohorts of the data. So I'm filtering them all. Data. So finally, here's the shape and here's the distribution. And here's where, so the pre-processing starts. So here is a function that I made sure that there was no data leakage, which means that there were no overlapping patients in the train, valid, and test set. And then the main thing we use for pre-processing for images, at least in the models that I've trained, is an image data generator, which doesn't save anything as it's not a TF, it's a Keras construct, not a TensorFlow construct. But it essentially, it compiles a list of file paths, and then it will load the data in batches. So it'll randomly split up the file paths, just like a TensorFlow data set would, into batches, and then it will load the data. So it's not loading your whole image data set into memory. And that's kind of what pre-processing looks like in this setting. So you set your parameters, your X column and Y column, and it'll create a data generator for you to train your models. So that's all I have on data pre-processing. Does anyone have any questions?
Cool. Chima?
I feel like I learned a lot. I learned a few new things with especially the first one. I didn't know one-hot encoding. We used it, I and Zach used it out of necessity. We didn't really think it was, I didn't think of it as a way to save memory. I wasn't thinking of it as another way to save memory. And the right record thing, is super useful. It's pretty useful as well. Good job overall.
Okay. Matt, I know we lost you at some point.
I'm so sorry. I lost internet connection. And you can see I'm in a different building because I ran. I'm so sorry. I thought it was really good. And I really liked when you were using the analogies of like the truck bringing things to the buildings.
Yeah.
I thought it was very useful to kind of like visualize and imagine it in like a real world way instead of just looking at numbers and talking about that type of computer process. But yeah, I thought it was a really great job when I was there. Again, I'm very sorry.
Yeah, no worries.
Okay. Zach, did you learn something from preparing for this chapter?
Yeah, I mean, I didn't really know what a TF record or a TensorFlow data set was, to be honest. Before, like I had read a little bit about the data sets, but I didn't know like the specific API or how to use them or really why we would use them over a data generator. But now I do know why. So I think in the future, I want to try building models and maybe using those instead of the data generators and seeing if that would improve performance, or at least I know like Chima and I have faced just waiting days for our models to train, and that maybe using these over the data generators will make it faster, the training process faster.
And you mentioned that you're gonna look if it works for imaging too, right? You're gonna research on it.
Yeah.
I would suggest that, it would be great to try out actually using them. Remember, we are just about to start a new fall semester, right? And next week we'll have new students. So I'm already getting emails for people joining the lab. And you guys said it was very painful, right? So trying to make the tooling easier for people to get started
Yeah.
is
Yeah.
like super important.
Yeah. Yeah.
Okay. Toby,
I
you even remember what machine learning is?
it's been long. Actually, it's been long, and Zach's session was amazing for me actually, because it's been long. I saw like an actual code that is not MATLAB, and even it's I think Zach's session also created that spark for me to learn TensorFlow, because what I did just copy and paste. And seeing his code and explanation of preprocessing on the fly. I've not used that before, and also this one hot vector. And this is like the first time I'm hearing about it. It was amazing to me. It was really amazing. Thank you, Zach.
Awesome. Cool. I think this was a hard topic, but it's an important topic. I hope that we, especially Matt, Zach, and Chima, you're going to spend a little bit more time, especially Chima, because Zach is kind of carving out what he's going to do, and just to try and think about the tooling to make it easier for people to get involved in machine learning. The bar is too high up, and right now we also have lots of projects, but if it takes people forever to get started, that's right. And then if you guys think about the paper on race, right, there are lots of people replicating experiments. So you kind of have, and people are asking, how exactly did you split this data, And so if you started, you remember we had said that it would be great if you could just say import memory CXR, right? And then you're like, boom, you're done, and that probably may be the first thing that I have you, Chima, do when you're back on either that or again, still, just because it makes it so easy for other people to do, because you'll find it's really important for you to be able to have like one-on-one, just something like you make it easy for the technology to use so that it's easy for you to focus on the problem at hand, right? Because soon the natural extension should be that now as you move on now to the next year is that you're reading papers and re-implementing them, right? There's lots of new techniques. So that's like the energy that I want to see. If the people see a problem, they're like, oh, I'm going to pick this up and go back and re-implement it. So if you abstract like the data loading and all those training things, and you keep very good code and good written notebooks, it's easy to come back and try new techniques, because all of you actually in the call need to be very technical more than myself, and so you need to be able to observe archive or observe papers with code and be like, okay, I see this, I'm gonna implement this and go back and implement it. So that's the progression I do want to see this year. It's much more forceful, but this is how you get papers into like the big CV conferences. Okay.
So I do have a question, especially I had a way, basically I had sort of an MVP thing. It worked. You could easily import it. But I was wondering if there is no concern, since it's on Hitty, right? It's okay, anyone can use it, right? There's no
Just on Hitty, so data cannot go anywhere. But if you want your MVP, you can also download public data sets, right? So we have Midrange, we have a ton, Checks Expert, and all these other data sets. So you could download them that way too.
Okay.
But, yeah.
Thank you.
Cool. Okay, who's teaching next? I know that Zach helped me with this one, right, Zach? I owe you.
Believe maybe me. I'll check.
Let's see. I have pinned it. So I don't, maybe Matt is not on there and Toby, but the presentation from the Imperial Group, right? I think Zach, you watched it.
Yeah, I watched it.
Was
really
amazing, right?
Yeah,
but it really just given we've read this book, right? When they were like, oh yeah, we use PCA, we use this. I mean, things were just like, oh, I know why. And you know, it was amazing. And it really shows like the broad strength. And that's something that we're very good at in our lab, so take advantage of that. And especially if you have a chance to be embedded in another learning group, right? Zach, you've had that, you've had that, right? You've worked with Leo, now you've worked with Luke. And now, I mean, it's just an amazing time. So you should absolutely take advantage of that. And it also builds your reputation and expands your network to whatever you want to do after this, okay? So yeah, so that talk, I recommend that you just from a tying things in the past, because it's been a while, you know, it will be amazing to just rewatch and be like, oh yeah, I see what they're doing, how they're processing their data to do like PCA or something like that. So, okay. And then I'm trying to look at who's coming up next.
It's pinned. I think was this chapter 3? This was chapter 13, correct?
Mm-hmm. So it's you, hands-on machine learning, chapter 14.
Yeah, chapter 14. That's perfect. That's perfect.
Oh, okay.
I got you.
Okay. Okay, cool.
Thank you guys. This was a nice break.
Okay. Yeah, okay. We are how many chapters away from our celebratory dinner, which we're gonna go for after we finish this book club?
I think 5 or 6. 5 or 6.
I actually have another book that we may read in future, not a computer science book, but it's How to Design Your Life. It's used in Stanford a lot, and I don't know, we may pick up that as another book to read together. But yeah. Okay, cool. Any other last comments? Toby, I'm gonna reach out to you maybe tomorrow, and we can just catch up. Zach, you doing okay?
Yeah, doing well.
Cool. I'm glad to have you back. I'm looking forward to a lot of work from you and lots of questions. So I know that I'll be speaking to you more often
Yes,
than
I'll be
not.
bothering you on Slack.
I know you will be, but it's never a bother. You know this, so I love it. And I look forward to learning from you too. Chima, what did you learn from your internship?
Very C#.